Algebra 2, Chapter 4, Section 5, Functions and Modeling, specifically direct proportionality. So today we're going to discuss functions and modeling with functions. Modeling is the process of applying what we know to the real world, essentially. And we're going to really do this with a family of functions called direct proportionality. So first let's talk about what direct proportionality means. A quantity is directly proportional to another quantity if quantity 1 is equal to some constant times the other quantity. And we can write this mathematically as Q equals the constant K times T. We call K the constant of proportionality. And again, it's constant with respect to T. We could write this with function notation a little bit more explicitly like this. And often we'll see the dot omitted. We will also be saying this in English, we will usually not bother saying directly. So we would just say a quantity Q is proportional to a quantity T. Often this idea of proportional to comes up so much that there's a shorthand way of writing it, this Greek letter alpha. And we think of this kind of like an equals. It means Q is proportional to T. Okay, so here you see this alpha. Q is proportional to T. And this is an equivalent and convenient way of writing the same thing. A property that's important to understand about proportionality is if we double the input, we double the output. And you can see this by putting in 2 times T into this abstract version of directly proportional to, and we see that we get K times 2 times T, which is 2KT, which is double the output. So doubling the input doubles the output. This was the old output. And another very important thing for modeling and understanding proportionality is that the constant of proportionality, K, is the rate of change for any interval. So it doesn't matter what interval of the input we take, the rate of change will always be the constant of proportionality, K. So let's apply this information to some problems. A car gets 25 miles per gallon. A, how far does the car travel on 1 gallon of gas? Well, we can see pretty easily here the car gets 25 miles a gallon. So if there's 1 gallon of gas, we get to go 25 miles. What about 2 gallons of gas? Well, we'll go double that, 50 miles. What about 10 gallons of gas? Well, we'll go 10 times the 25, or 250 miles. What about 25 gallons? Here we might want to start thinking about the math that we're doing. We're doing 25 times whatever number here. So this was 25 times 1. This was 25 times 2, 25 times 10. So the answer will be 25 times 25. 25 gallons, 25 miles. And that is 625 miles. B. Express the distance d in miles traveled, sorry for the typo, as a function of the number of gallons G of gas used. Okay, so the distance traveled as a function of the number of gallons. So the function is going to be of G, so the name of the function is d, or distance. Our output is going to be distance, miles. And G is the number of gallons that we use. That's our input. So now we can say, as a definition, let d of G be 25G, which is what we just saw us doing. 25 times the number of gallons. 25 is our constant of proportionality. And we see that 25 must be the constant of proportionality because this follows K times, and again, the letter we use for the input could be anything. Here it's G. And we'll put a dot here to make this not look like kilograms. Okay, so sometimes that's why we add a dot, is to disambiguate. So this looks just like a proportionality. We have constant times variable is output. That's why it must be proportional to. So let's go over some examples of identifying direct proportionalities. This question says, does this function represent a direct proportionality? If so, give the constant k. So here it's pretty simple. We have a number times our input, so yes. And the constant k is 19. For b, we have this is a little trickier. Let's rearrange this to be 1/53rd times x, the rule. And now it's clearly a direct proportionality, yes. The constant is 1/53rd. C. F of a is 2a plus 5a. Well, 2a plus 5a equals 7a, which is yes. The k is 7. So sometimes we'll have to simplify what we've done in order to get the answer. D. U of t is square root of 5t. Well, here again, square root of 5 doesn't go, the square root's not going over the t, so it's just a plain old t. And the square root of 5 is just the number, so the answer is yes. Constant k is the square root of 5. E. N pi squared, and n is the input. So that gives us yes, because the variable is n. The k is pi squared. F. Here are inputs t. We have 2 plus 5t. This doesn't fit into the direct proportionality because we just don't have a simple number times the input. We have this extra 2 plus. So the answer here is no. And we weren't told to do anything extra if the answer was no. Let's do another problem. A graduate assistant at a college earns $80 for 10 hours of work. Express her earnings as a function of hours worked. What is the constant of proportionality, and what is its practical interpretation? To do this problem, we need to think about the units and to think about what's going on. So we have a graduate assistant earning $80 for 10 hours of work. Okay, so if she works 10 hours, she gets $80. So how much does she get per hour? Well, we can take $80, divide that by 10 hours. And here I'm putting the units with the numbers to help do unit analysis, to help understand the units. So this equals 8 over 1, which we would just call $8 an hour. And we would write this in our shorthand. And remember, dollars goes in front of the number, which is different than every other unit. $8 an hour. So that would be her rate, her hourly rate. So rate because it has to do with something over time. And so now we can write a function. I'm going to use capital E for earnings and H for hours. She makes $8 for each hour. What is the constant of proportionality? Well, it's 8. And what is its practical interpretation? It's the hourly rate. $8 an hour, the hourly rate. Another example, a person's heart mass is roughly proportional to his or her body mass. A person with a body mass of 70 kilograms has a heart mass of 0.42 kilograms. Estimate the constant of proportionality. So here we have the heart mass, we're going to call this capital H, is proportional to, roughly, the body mass, which I'm going to write just as a lowercase m. So that would mean that we have the heart mass as a function of the body mass. So that means it's directly proportional to, we must have some constant of proportionality times the body mass. And again, I'm going to put a dot here because km looks like kilometers. So we can write an equation here to find k. So we can put heart mass, 0.42, the output, when we have an input of 70 kilograms, the body mass, and we end up with an equation which we can solve for k. So k must be 0.42 over 70. Using a calculator, 0.42 over 70, 0.42 over 70 equals 0.006. So that's what k will equal. K equals 0.006. And this was kilograms per kilogram, which would mean the units would cancel. So this is a unitless constant, k. There's no units for this particular constant. So now we can write 0.006 for k times m. Now, estimate the heart mass of a person with a body mass of 60 kilograms. Then, so let's write a new equation. So we want to find out what is the heart mass if we put in 60. Putting in 60 times 0.006, we get 0.36 kilograms of heart mass. That's the answer to part B. The answer to part A was 0.006. One more example. The data rate of an internet connection is the rate in bits per second that data, such as a web page, an image, a streaming video, can be downloaded across the connection. Suppose the download rate is 20 megabits per second. How long does it take to download a 1 gigabyte file? And then we have this unit issue. Use the fact that there are 1024 cubed bytes in a gigabyte and 8 bits in a byte. Note that the M, the capital M, in megabits per second is SI, or scientific units. In other words, 1,000,000 bits per second. So we have a data rate. Okay, so let's first think about the constant of proportionality. The data rate is the constant of proportionality. It's 20. So we have the how long in this time, where we're wanting time to be our output. Time given the quantity of data, or the number of bits. I'll just write little b for bits. Okay, so in this case we want to know time. We have the opposite given as our constant. So we're told 20 megabits per second, but here we want the seconds to be the thing we get out, not the bits. We want to put bits in, so bits needs to go on the bottom. So here we have 20 mega, which meant million. So 20 million bits per second. But we want seconds per bit, so we can multiply by bits and get out seconds. Okay, so what we need to do then is to invert this to get, and we can write inversion quickly as -1, which we'll talk about that later. Let's just think about dividing all of this under a 1. So we would have 1 over 20 million. What is 1 over 20 million? Well, it's 1 over 20 but in nanoseconds. So if we do 1 over 20 million, oh, you probably can't see that, 1 over 20 million. 1, 2, 3, 1, 2, 3, 20. We get 0.0000005, which is 50 nanoseconds. Okay, so this would be 50 nanoseconds per bit. Okay, so it takes 50 nanoseconds to transmit 1 bit. Times the number of bits b. That'll tell us how long it takes to download something. Now we have to think about putting in our input, which was 1 gigabyte. So we're told 50 nanoseconds per bit times 1 gigabyte. And a gigabyte is not a gigabyte. It's 1024 cubed. Now we often say gigabyte and are loose with this, but we want to be careful here because data rates are measured in plain old megabits, 1000 times 1000, not mebi bits, which is the 1024 based prefix. So we have 1 gigabyte file, and we need to convert our units. So we have 1 gigabyte. We need this to be bits. So to make bits, first we can turn gigabytes into bits using this information. So we have the fact that we have 1024 cubed. Sorry, I've got this backwards. Erase that. We have 1024 cubed bytes in 1 gigabyte. We're arranging this so that these will cancel. Gigabytes cancels with gigabytes. We're left with bytes. So when we multiply our 50 nanoseconds per bit times this, we have not canceled yet because we have bytes and bits. So now we have to think about how many bits are in a byte. We're told there's 8 bits in 1 byte. Now our byte will cancel, our bits will cancel, and we'll just be left with time in nanoseconds. Now, we probably want to think about time in seconds. So to convert from nanoseconds to seconds, just remember there's 1 million nanoseconds per second. And that's not right. It's 1 billion. Right, this came from billion. There are 1 billion nanoseconds per second. There's 1 million microseconds and 1,000 milliseconds. So we have 1 billion nanoseconds per second. That'll get rid of the nanoseconds. You can also just think of nano and a 1, but I'm sorry. So we're left with seconds. So this is called unit analysis, when we write the units with our fractions and we cancel units as if they were algebra variables. That helps us get our units straight and to help us figure out what our output should be. So now all we need to do is to pull up a calculator and do this calculation. So going back to our calculator, we have 50 times 1, which, I'm sorry, we've got that wrong. Let's look at this again. We weren't given 1 gigabyte, were we? Yes, we were. Double check. 1 gigabyte. So if this were 5, we'd put 5 here. If this were 20, we'd put 20 here. But we only needed to find 1 gigabyte. So 50 times 1, which is just going to be 50, times 1024 cubed. Remember, 1024 cubed is just 1024 times 1024 times 1024 times 8 bits per byte divided by 1 million. Or sorry, 1 billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. And that gives us an answer. 429.5. We'll round it to the 4 significant digits. 429.5 seconds. Now we could be done with it at this point, but we don't usually think about seconds when past 1 minute. So let's think about how many minutes and how many seconds this is. So if we divide by 60, we get the number of minutes, 7 minutes, 7.158 minutes. So 7 minutes. And if we subtract the number of seconds 7 minutes takes off 429.5, which would be 7 times 60, we'll get how many seconds? 9.5. So 7 minutes and 9.5 seconds. That's how long it will take to download a 1 gigabyte file over this 20 megabit per second connection. Now let's talk about graphing these direct proportionalities. The functions, and these are like a family of functions. So the functions whose rule have as their rule direct proportionality are a part of the direct proportionality family of functions. So the constant of proportionality k is a parameter of the function family. Okay, that means that all of the direct proportionalities share certain common characteristics. So we put them in one family of functions. What differentiates them is what this constant is. So the graph of any function that is a direct proportionality, or in the family of direct proportionalities, shares all these properties. The graph is a straight line. Okay, so if we graph a direct proportionality, it will be a straight line. The line goes through the origin. Okay, so it'll go through 0, 0. And the slope of the line is the constant of proportionality. Okay, we'll talk more about slope in the next video. But we can sketch any proportionality, direct proportionality, using these rules. That goes through the origin, and it is a straight line, and its slope is going to be given by whatever that value of k was. So if k is positive, it'll go up as we go over. If it's negative, it'll go down. If k were 0, which would be kind of silly, we would just have the input axis. There would be no output. It would always be 0. There's no way to get an up and down line as a function because only one output for any input. So putting in 0, we can only ever get one thing out.